All right, in this video we're going to talk about the derivative of the natural log function. So we just recently talked about the derivative of the natural exponential. Okay, so it makes sense that now we're going to talk about the derivative of the natural logarithm. Those are two inverse functions. By the way, fair warning: if you need to refresh your knowledge of logarithms, of exponentials, of properties of logarithms, properties of exponents, how those are all related, do so, because we're going to need a few of those properties right now in a few minutes. And then you'll need those properties periodically when you're solving these equations, doing these derivatives. We'll need those properties. Okay, so I have a college algebra book that I wrote that I use that I'll probably post on Blackboard. If I haven't done so, ask me for it, or go online and use whatever resources online that you have. There's tons of YouTube videos and stuff and such where you can relearn properties of logs. So let's jump in. First of all, derivative of natural log is 1 over x. Now, to me, when I first see it, I think that's interesting because that's telling me that the derivative of a logarithm, here a natural logarithm, is equal to 1 over x. So you have a logarithm, it's a special class of function called a transcendental function. It's in the same class of like exponentials and trig functions. So this is a special class called transcendental functions, but its derivative is 1 over x, which is just a pretty basic, it's called an algebraic function. So that's interesting to me, that essentially the derivative of a logarithm, of natural logarithm, does not have logarithms in it. To me, that's unexpected. I think it's a pretty cool little property. At any rate, let's look at where that result comes from. Now, you might have guessed it. Where does it come from? The limit definition of the derivative. That's where it always comes from. So let's take a look. If you want to show what the derivative of natural log is, you apply the limit definition. The limit is delta x goes to 0 of what? F of x plus delta x. Sorry, it wasn't coming out. The limit is delta x goes to 0 of f of x plus delta x. There we go. Minus f of x over delta x. So this is the exact same form that we always talk about when we do the limit definition. Okay. Now, what's up next? We apply the logarithm quotient rule, the quotient property. This is what I was just referring to. So this property says if you have the difference of two logarithms, same base of course, that you can condense that into a single logarithm by taking the quotient of the two arguments. So here notice that we take the quotient of x plus delta x and x. Now the next step is not really simplification at all, it's more of just rewriting, strategic rewriting. We separate the fraction. Remember, if you have 1 over or x plus delta x over x, we can rewrite that as x over x plus delta x over x. And then I can simplify that at the next step. Okay? Why? Well, I'm trying to eventually take advantage of a specific form. So that's why I'm rewriting it, because in the back of my mind, what I have in the back of my mind is this. I have, here, let's get that stray mark out of the way, that special limit from the previous chapter about limits is the limit as x goes to 0 of 1 plus x to the 1 over x power. Remember, what does that equal? It equals e, just like we used in the previous video. So that's what I have in the back of my head, so I'm kind of trying to eventually work my way toward that. Of course, though, I have delta x's right now, but remember, that's just a superficial difference. So notice that if I have the natural log of 1 plus delta x over x, all over delta x. And now what I'm going to do, instead of writing this as a quotient, I can write this as, okay, so I have natural log of 1 plus delta x over all over delta x. But I can rewrite, anytime you have a division, a quotient, you can write that as a product instead. So I can say instead this is equal to 1 over delta x times natural log 1 plus delta x over x, like so. So all I've done is I'm writing it as the product of a fraction and that numerator instead of writing it in regular old fraction form. Now, why am I doing this? Because remember the power rule for logarithms. If you have a scalar multiple out front, you can move that to the exponent of your argument. And we could say this is equal to natural log 1 plus delta x over x raised to the 1 over delta x power. So I can rewrite this using it's called the power rule, power property of logarithms. Okay? So, and again, my whole point of this is eventually I want to get to use that. Oh, sorry. I just realized that my picture was blocking out the answer there. This all equals, see if I can squeeze it in. Here, I'll just do this. Equals E. I'll write it backwards. Okay? That's what I want to use. If I can get this particular limit, I know it's equal to E. Now, we're going to have to do something in this next step that you don't have to do in every limit, but you do have to do occasionally. It's called a change of variable. Now, we will become familiar with this technique. You do it a little bit in college algebra whenever you're trying to do something like solve a quadratic form equation, like something that looks like it's quadratic but not quite. You oftentimes will use like U substitution to do that. It's to rewrite it so that you can use properties of quadratics, and then you back substitute at the end. We're kind of doing a similar thing here. We're going to change the variable. So instead of taking the limit as delta x goes to 0, I'm going to let t equal delta x over x. Now, why am I even doing this? Again, I'm trying to get a limit. Why did I put a delta x there? I'm trying to get this form. 1 plus something raised to the 1 over that something power. So right now, I have an exponent of 1 over delta x, and I have this x plus delta x over x. I just want a regular old variable there. In fact, I want t there. So what I'm going to do is I'm going to let this equal t. That way I'll just get a plain old t there, which is kind of what I want right there. Again, the variable t versus x does not matter. Okay, so I apply this substitution. Now, what we also have to consider the fact that what is the behavior of t as delta x goes to 0. Okay, so as delta x gets smaller, closer and closer to 0, well, what happens to t? Well, if the right-hand side gets closer and closer to 0, then t, the left-hand side, has to also get closer and closer to 0. So my point being there that we're still going to take the limit as t goes to 0. Now, I just looked ahead on my next line of my notes and realized I made a mistake. I'll fix this before you see the notes, but that's supposed to be a t there because we have now changed variables, not delta x. So I'll fix that before you even see this, but those all need to be t's because now we're taking the limit as t goes to 0. And also notice that we need to substitute in for delta x because we have to change the limit completely over to t. We can't have, now that we're changing the variable, we can't have t's and delta x's mixed up in the same limit. So we need to switch all of our delta x's to t's. And what does this substitution tell us that delta x equals? Well, if t equals delta x over x, then if you multiply both sides by x, you get delta x is t times x. So that is where delta x equals t times x. That's where that 1 over t times x comes from. Okay? So now we change over. We're now taking the limit as t goes to 0. We apply the substitution, and now we have this new limit to work with. Now, it looks a little better to me. You know, anytime you can avoid delta x's, it kind of looks better. It looks simpler, but we're not quite there yet because we want to apply this special limit up here. this special limit. Okay, we're not quite there yet. Not quite there yet. We have almost there. We have 1 plus t to the 1 over tx. But remember, we can use properties of exponents. We have a property that says a to the, let me fix that, m times n equals a to the m to the n power, or vice versa. Equals a to the n to the m power. In other words, you can rewrite and you can reverse the order of the powers. Why? Because when you have an exponential expression raised to another exponent, you multiply the exponents. Well, multiplication of real numbers is commutative, so it doesn't matter the order there. So what we can do is we can rewrite this as 1 plus t to the 1 over t and get exactly what we're looking for, just like we have up here in the top right hand by my picture, that 1 plus a variable to the 1 over that variable power, and we can do the 1 over x on the outside. Why is that important? It's important because we have a composition limit property. The composition limit property says that we can take the limit of the inside portion of the function. So now we have two functions. We have an inside and we have an outside part. And we can take the limit of the inside part, as I've done here. Now we're taking the limit inside the natural log function. And now I have that exact form that I've been after. The limit as t goes to 0 of 1 plus t to the 1 over t power. And what do I know that equals? I know it equals e. Okay? So now that limit equals e, okay, well now I have, let me get over here, erase this. That whole inside portion turns to e. So now I have e, natural log of e to the 1 over x. But what we know about natural log and e, they're inverse functions. So we know that natural log of e to anything, we'll say b, is just equal to b, because they're inverse functions. So whatever is in the exponent here, that's what the whole expression simplifies to. Here we have a 1 over x. And so this expression simplifies to 1 over x, which is what the theorem above 2.52 said we were looking for. So the derivative of natural log x is 1 over x. Okay, that's a pretty intense little proof there, but as long as you remember your properties of logarithms, it works out pretty nicely. Okay, now let's do a couple examples with this in mind. Okay, so we have part A here. We have the derivative of a product. We have x cubed times natural log x. So we need to use the product rule. So let's see what we can come up with. F prime of x. Apply the product rule. Don't skip the application of the product rule. Don't try to do all the steps in your head. We're going to do the derivative with respect to x of x cubed times natural log x, plus the derivative with respect to x of natural log x times x cubed. Don't be tempted to skip that step. You're supposed to always show you all your work on tests for sure, but be in the habit when you're doing your homework, because the habits you build when you're doing your homework is what you're going to do in the test, and you got to be really careful, especially when you're testing. All right, so now we actually take those individual derivatives. So the derivative of x cubed is 3x squared times that natural log x plus, now what's the derivative of natural log? Well, we just learned it's 1 over x times x cubed that was already there. Okay, if I could write a good 3. There we go. Well, that's not a good 3. Come on, there we go. And now we just simplify. Maybe factor if we can. So the first two terms, just kind of leave them, or first term, just leave it alone. There's nothing really to do there. But the second term, we have 1 over x times x squared, sorry, times x cubed, equals x squared. Properties of exponents. And I'm going to factor it just because. If we can factor out an x squared, that leaves us with 3 natural log x plus 1. Okay? Again, why that factor? Because a lot of times it's good to have that factored form, because a lot of times we're just going to go ahead and set the derivative equal to 0 and solve, which you need factored form when we actually have to do that. So it's a good habit to be in. All right, let's look at B. G prime. What is G? Well, G is a quotient of two functions. Thus requires the quotient rule. So let's see. Derivative of the first function, which is natural log x, times the second function, x squared, minus the derivative of the bottom function. I think I said second function earlier. Bottom function, x squared times natural log x over x squared squared. All right, that's the quotient rule. Let's see what we get when we simplify, or actually differentiate now these individual derivatives. Natural log x has a derivative of 1 over x times x squared minus, okay, the derivative of x squared is 2x times natural log x. We can go ahead and say x to the fourth, since x squared squared, you multiply and get x to the fourth. Let's see if we simplify a little bit here. We have what? 1 over x times x squared, so you have a single power on the bottom and a square on the top, same base, so you subtract 2 minus 1, of course, and you get just x minus 2x natural log x over x to the fourth. Now, okay, we can definitely simplify this by factoring out of the numerator an x. Now, be careful here. Always be careful when you're factoring and dividing out common factors. I see a lot of students get to this point and just start canceling stuff off everywhere. Don't do that. Factor, then divide or cancel. Okay, so we factor out an x. That gives us 1 minus 2 natural log x on the numerator, x to the fourth on the denominator. And now we can say, okay, there's a single x up there. We can say that's now a third power on the denominator if we cancel one x off the top and the bottom. So our final answer here is 1 minus 2 natural log x over x cubed. All right. Oh, this is an interesting question. I like that I put, actually C and D are here interesting. I forgot I put these on here. Now, what do you notice about C and D, which has not been true about any other function we have dealt with so far this semester? Think about it. 5, 4, 3, 2, 1. How are they different? They're composite. Natural log of 2x has an inside function that's not just a plain x. It's a composite function. Natural log of 4 over x. It's composite. The inside function is not just a plain x. All the functions we've worked with so far have not been composite, have been non-composite. Now here's the thing. In general, for a composite function, you need something called the chain rule. But we have not done the chain rule yet. That's why we haven't done composite functions. But turns out with logarithms, you can kind of work your way around that because of the properties of logarithms. So to do this, now in a few sections, we'll cover the chain rule, and I'll give you another way to solve this. But for the time being, without the chain rule, you have no option except to apply properties of logarithms. That is, what do we know we can write this as? Okay, we have the product property of logarithms says, well, I'll do it for natural log. Natural log of x times y equals natural log x plus natural log y. The quotient rule says natural log of x divided by y is natural log x minus natural log y. So how can I rewrite the function h? Well, I could say that's natural log of 2 plus natural log of x. Guess what? It's not composite anymore. And so now I can take the derivative of those two terms individually according to the sum difference rule. So I could say h prime is the derivative with respect to x of the first term, natural log 2, plus the derivative, oh, not natural log just yet, plus the derivative of that second term, natural log x. Now here's where I said, sometimes taking the derivative of a constant function can be kind of tricky, but remember, natural log of 2 is it's a constant. Type into your calculator. It's just some number. What is the number? It's some number such that e raised to that number equals 2. So I guess it's a number that's smaller than, smaller than 1, because e to the first power would be 2.718. So to get 2 as the result would have to be an exponent smaller than 1. So I don't know. Yeah, let's see. E natural log of 2 is just some number. It is approximately 0.6931. It's just a constant. So the derivative is 0. And then the derivative of natural log is 1 over x. So 1 over x. So even though it's composite and we would normally need something called the chain rule that we haven't talked about yet, you don't need that right now because we can rewrite it. Okay, let's do the same thing for f. In part D, we can rewrite this as f of x, so no calculus just yet. F of x is natural log of 4 minus natural log of x. Okay, and so now to find f prime, I use the sum difference rule, which says I can take the derivatives of these terms individually. And again, natural log of 4, okay, think about it, natural log of 4 is some number such that e raised to that number is 4. Okay, so if e is about 2.7, e to the first power would be about 2.7. E squared would be kind of close to 9. So natural log of 4 is some number between 1 and 2. It's just a number. It's a constant. And the derivative of a constant is 0. Minus derivative of natural log, 1 over x. So our answer is 1. Oh, no, it's not 1 over x. Fail. Negative 1 over x. There we go. Negative 1 over x. All right. So now we've covered exponentials, natural exponentials, and we've covered natural logarithms. The logical next step is to do non-natural exponentials and non-natural logarithms. We have to tweak our properties a little bit, but that's where we're going to go next. Let me know if you have any questions. See you soon.